Hello. Can everyone hear me? Yes. Hello, everyone. My name is David. I'm very pleased to be here, and I'm very pleased that you're sticking around for the last talk in the conference. I'm going to be talking with you about Akka and how it can be a best friend forever for your backend-for-frontend, also known as a BFF. If you've never heard of a BFF, don't worry. We're going to go through that as well, so you should be able to learn something. So, this talk may strike you as a little different from the others we've seen. I've said to a number of people that I feel like I sort of snuck into this conference. Nobody really noticed, and that's because the code I'm going to show you is perhaps a sort of different kind of functional. I'm going to warn you up front. There are side effects. They are isolated, but perhaps not in any sort of I/O monad. And I'm using Akka. We've heard a couple presenters say that, X is better than Akka, and don't use Scala futures because, they're not good. I'm not here to say which is better, rather just to sort of relate an experience that we've had. I also work on an infrastructure team, so a few places in this talk, we're going to hear about things like load balancers. And this is a little different, so hopefully it's a good change of pace for a Friday afternoon talk. Before we get started, I want to give credit to my whole team. I work on the core team at PagerDuty, and so do these fine people, and we work on all of our projects together. So what are we talking about? Here's the plan. First, I'm going to describe the BFF pattern and what it looks like at PagerDuty. Then we're going to talk about using Akka HTTP to proxy and route requests. After that, we'll talk about using Akka Streams to enable live updating of our UIs. Finally, I'll share some results from deploying our code to production. So let's see a show of hands. How many people have heard of the BFF pattern? Some people, OK. How many of you heard about it the first time you saw my talk abstract? All right. So this will be a bit of a learning experience for some people, and maybe other people will just already know these things, but that's OK too. So this is a diagram of how BFFs might fit into a typical microservices architecture. We have 3 BFFs shown here. So each BFF receives requests and routes it appropriately to a backend service. So we can sort of take the example of an online store. There's a service that has the user profile data, so requests that for that profile would be routed to that service. Likewise, requests for the user's shopping cart might go to a different backend service. Each BFF can route requests appropriately. Now, after seeing this diagram, you might be tempted to think, OK, BFFs are basically about routing for microservices. This is a fancy new word for an API gateway. And why do we need 3? For contrast, here's what the diagram looks like with an API gateway. A single service that serves all types of clients. So the difference between these 2 diagrams can be summed up in one word, and that's focus. BFFs are really about focusing on a specific user experience or a specific front end. So you saw that there were 3 BFFs in the previous slide, and that's because there are 3 user experiences shown. There's a mobile experience, a website experience, and a developer API. Each of these front ends has different needs. So for example, on mobile, you have a smaller screen, so probably less data is displayed. It is wasteful to send data over the wire that's never going to be used, especially in North America where we have terrible data plans. So a mobile BFF might transform responses from your system to remove unnecessary data that's not displayed. Without a BFF, you kind of have 2 options. You end up putting that kind of front-end logic into each back-end service itself, or you can cram that logic for all your front ends into an API gateway. Neither are great ideas. One sort of spreads knowledge about your front ends across all your services. The other puts a bunch of unrelated front-end logic together where it doesn't really need to be. BFFs really allow us to encapsulate all that front-end specific stuff into one place while maintaining focus. We're really trying to not violate the single responsibility principle here. So I just mentioned routing and response transformation, but there are many other things that you might want to do with a BFF. Now, some of these are a bit more controversial, and this being a relatively new pattern, there's lots of opinions floating around. So don't take my word for it necessarily, but here's some thoughts. Let's take API aggregation. Maybe you have a developer API that combines data from multiple backend services. So say the user API also returns data about the user's shopping cart. So how do you put that data together? Well, one answer might be making parallel calls to those separate backend services from the BFF, and then aggregating the responses into a single API response to your user. Or take authentication. The developers of these backends care about authentication, but they don't necessarily want to write code for it. And even if they do write code for it, chances are someone will eventually get it wrong, and that's a bad thing. So you can push that sort of generic edge concern into the BFF layer. You can make it easy for backend developers to concentrate on their features without worrying about things like authentication. It's the same thing for rate limiting. So it's a generic concern that just needs to be done, but it shouldn't be done by everyone in different ways and different places. Now, what about live UIs? I'm going to say liveness throughout this presentation, but what I really mean is the ability of an interface to automatically reflect up-to-date information without any intervention from the user. So if you're on a website, you don't have to hit refresh. If you're on a mobile app, you don't have to swipe down. Well, different front ends have different liveness needs as well. The example from previously still applies. Mobile needs less live data, and maybe it needs it to look a little different than the website does. Is there a way that we could use a BFF to customize a live user experience? Well, we're going to find out. So, given that you can do many things with a BFF, I would like to share a bit more about what it has meant for PagerDuty in the last year. Any guesses about what's on this slide? Well, it's a monolith. PD, like many other companies, started with a monolithic Ruby on Rails application, and over time, we've outgrown it. We have embraced microservices while trying to put less code into our monolith. It can be difficult to get rid of a monolith, though. By definition, a monolith is a very large piece of software, and it probably plays some crucial roles in the operation of your system. You can't just split it into 100 microservices all at once and delete the monolith repo. Instead, what you end up doing is you chip away small pieces of where it makes sense. You break down that monolith gradually. And this means that your monolith and your microservices are going to coexist for quite a while. Some traffic will continue to go to your monolith, while other traffic will go to your new services. So how do you manage that gradual shift of traffic? Now, maybe some of you are looking at this photo in a very confused manner, but what we have here is a strangler vine, and I'm making reference to the strangler pattern. So we've been using BFFs as stranglers, actually, meaning that we have placed them in front of our monolith, and slowly but surely we're moving traffic from that monolith to our new services. Traffic in this analogy is kind of like the oxygen for our monolith. Eventually it will have none or it will have less. It's going to look much different than it does today, or maybe it won't exist at all. So to make this strangler pattern work in our BFFs, there's a few important things that we absolutely must have from the start. Number one, HTTP routing and proxying. These new microservices must have authenticated traffic. Obviously, we need to know when to direct traffic to our monolith and when to direct traffic to our microservice. Number two is authentication. So these new microservices must have authenticated traffic since they serve user-facing APIs. But they don't necessarily want to know how to do the authentication themselves. And lastly, and this is not really strangler pattern related, but we've tackled live UIs at the same time. So this is probably the most controversial piece when it comes to BFFs. I'm actually unaware of other companies doing it this way, but I would love to hear about it if you are. But when you think about it, there's some logic here. A BFF is basically a gateway and a transformer for all of the front end's traffic. So why should we limit it to traditional HTTP request response patterns? Why is liveness traffic really any different? The point I'm trying to make here is that the underlying transport mechanism doesn't really matter. What's important is that the BFF is receiving and sending traffic for that specific front end that it's built for. So that traffic could be, it could go in any direction, and it could use any sort of protocol. It could be HTTP, WebSockets, or even something like Thrift, although I hate Thrift, so let's not go there. These three pieces of functionality are going to be the focus of this presentation. So let's have a bit more detailed look at each of them. This diagram depicts the HTTP routing and proxying functionality. So at PD, incoming requests go to different backends, whether it's the monolith or a new microservice. And this is pretty easy to understand, but perhaps not so easy to implement. In this presentation, we're going to walk through how routing and proxying can be done with Akka HTTP. And like I said, these microservices need to have authentication done for them. So in our system, the BFFs actually extract credentials from an incoming request. Then they validate those credentials by calling an authentication service. Finally, if those credentials are good, they're valid, the BFF attaches a header to the request with the authenticated data. So for example, a user ID might be included with the incoming request once it leaves the BFF. The upstream service then just needs to read that header with the user ID data, and it doesn't need to do any authentication itself. Now, some of you are thinking that has security implications, and it absolutely does. In the interest of time, I'm not going to go into much detail here, but the one way to do it is to sign your header that you're sending from your BFF cryptographically. So the upstream service can verify the signature of the header to ensure that the BFF wrote it and it can be trusted. Now, actually, when it comes to code, this is the most boring part. I'm not going to really talk about it beyond this, but just know, this is a thing that you should probably do. The last piece of functionality in our BFFs is Liveness, updating our live UIs. We use Apache Kafka pretty extensively at PD, and it's pretty natural that we have a Kafka topic or many Kafka topics where our services can publish new information that might need to be published to a user interface. So these topics are basically like a fire hose of change events for many of the entities managed by our backend services. Our BFFs can consume from that topic or topics, transform the data as needed, and then push it to a front end through a WebSocket. This is the second interesting bit of code that we have in our BFFs, and we're going to see later on how Akka Streams gives you great building blocks to get this done. Okay, so now that everyone hopefully understands the BFF pattern and how it can be used, let's dig into some code. I've been saying proxying and routing up until now. Really the interesting part is the proxy portion, but we will see how to do routing as well. So let's zoom in on a single BFF. It can receive requests that go to any number of upstream services. The first question is, where are those services? If the BFF determines that a request should go to the monolith, what IP and port should it forward the request to? This is a standard problem. It has a standard answer, and that's service discovery. Service discovery can tell us the IP and port that the monolith is available at, for example. Now, because those service instances might go up and down, this address information is pretty dynamic. You need a way to update it constantly without disrupting your BFF. Restarting the BFF every few minutes is not really an option here. So the way we typically handle this, and other people do probably too, is we abstract that service discovery away from our application, whether it's a BFF or something else. So in this diagram, you see HA proxy, and it's getting information from our service discovery mechanism. There's nothing in particular here about HA proxy that makes it special or good, but it can do things like hot reload your configuration and things like that. So the real point of this slide that I want everyone to remember is that from the BFF's point of view, the monolith is available at localhost and some port that it might assign, so port 3000, say. A microservice might be available at port 4000, also on localhost. All right, some code. So let's say we have an incident API, and we want all of the incident API requests to go to the monolith at port 3000. Now, this is like the sort of routing part. Incident API requests all start with the same path, API/incidents. There's many URLs below that, but that's sort of the prefix. And so Akka HTTP has this easy way to capture all those requests using the standard routing DSL, and that's the path prefix up there. We then extract the request object with a standard Akka directive and pass it to a proxy function along with the destination port. So if we think about what the proxy has to do without defining it yet, it's pretty simple. It accepts a request and a port, and it returns a future HTTP response, which comes from the upstream service. This is, pretty simple, right? We just need to define that proxy function now. So here's what the proxy function might look like. We build an HTTP authority for our target, which is just the fancy HTTP way of saying host and port. And of course, again, we're talking to our local HA proxy instance. So our host is just localhost. The port is the one provided as an argument to the function. We then rebuild the URI of the incoming request, and we rebuild the incoming request object itself. Notice that Akka has a pretty functional API here. All the objects are immutable. If we want to change them, we simply build new objects. So we have a request that's ready to be proxied to the upstream. But how do we actually send it? So Akka HTTP has a client as well as a server. And crucially, this is the very important part, it uses the exact same immutable HTTP model as the server does. So we can simply pass our proxy request to the client, and it returns a future HTTP response. This is exactly what we want. This is exactly what the server needs to complete the request. Now, for the sake of simplicity, I've glossed over a couple things here. So, for example, normally the HTTP client is injected so that we can stub it out and things like that. But this is actually very similar to the code that we have in production. Personally, I was pretty shocked about this, how easy it was. Just like built an HTTP proxy in like a few lines. And I felt like surely, we're doing something wrong. And we are. It's pretty subtle though. This will compile, it'll work for a while, but eventually you're gonna run into trouble. Does anyone see what is wrong with this? Nobody, all right. So there's this thing called the streaming nature of request and response entities. I've been told that I can be a very literal person. I guess this slide is pretty good evidence of that. So anyway, if you Google that phrase, you'll get a very good description from the Akka Docs, which I highly recommend you read. But in essence, what this means is that the body of an HTTP request or response is not eagerly consumed into memory by Akka. Eagerly consuming is what many other clients and servers will do. So this feature can be a bit surprising at first. What happens is if an HTTP entity is not consumed by your code, Akka will interpret that as back pressure. It will actually stop the other side of the TCP connection from sending data. So in Akka HTTP, you must always either consume the body or explicitly discard it. Now, in our code, there is no explicit consuming or discarding. So how does this affect our proxy? Well, to answer that question, let's dig a little further. So we were using the single request method on the client in our proxy code. And that request is sent to a host connection pool. The host connection pool is really like a collection of TCP connections to our target upstream service. And each connection takes up what's called a slot. Whenever a request is submitted to this pool interface, one of two things can happen. Number one, if there are free slots in the connection pool, the request is immediately sent to that slot for dispatch to the upstream. Number two, if all slots are busy with ongoing requests, the submitted request is put into a ring buffer so that it can be dispatched once one of the slots becomes free. So the symptom that we actually experienced with the code that we just saw there is an exception telling us that that ring buffer was full. And once we saw that exception, no more requests could be sent out until we actually restarted the process. So what that means is, it wasn't just some big traffic spike. We didn't need to make the buffer bigger. It was permanently down. After a bit of digging, we discovered that we were hitting this sort of streaming entities problem. Over time, we would have quite a few instances of a user client disconnecting from the BFF before consuming the HTTP entity. And in practice, what this means is that the slot in the host connection pool is never freed. It waits forever for something to consume that HTTP entity. So over time, the connection pool leaks connections, and it's eventually going to leak all of them. Once there's no available connections, the ring buffer fills up very quickly. So of course, this happens no matter how big you make your pool or your buffer. So here's an illustration of that scenario. So a user client makes a request to the BFF, which forwards the request to the upstream microservice. After some time, the microservice responds, and perhaps the response is big enough that it will be streamed rather than sent in one piece. And the case that we're not handling is that the user client disconnects before it receives or consumes the response. This is a corner case, but it will certainly happen. So let's step back a bit and think about how this normally works in the happy path. So in our example code, there was no explicit consumption of the HTTP entity. And that's because ultimately, the user client is the consumer of the streamed response. When the client tries to consume the HTTP entity, that demand is essentially proxied through our server to the Akka HTTP client. So what's happening is that the user client consumes the entity from the upstream microservice through the BFF. So if that user client never consumes the entity, it never signals that demand, then we have this problem with leaking connections. So the question is, how do we fix this? Well, here's one solution. To be honest, I'm not entirely satisfied with it, but it does work very well. And so what we're doing here is in our proxy code, we simply eagerly consume the HTTP entity. This frees up the connection as soon as possible, even if the client disconnects or doesn't end up consuming the body. And naturally, consuming the entity is an async operation, so this code just flattens some futures with flatMap to return the expected future HTTP response. So still not too bad still. We just added a few lines. Who thinks this is ready to ship to production? Hands? Yeah, yeah, well, I mean, it's not. There's one more problem. It has to do with how Akka chooses a connection when it sends a request. And a bit of a spoiler here, it's not evenly distributed, so I'm going to call this connection bias. So let's take another look at our earlier diagram, including HA proxy. One microservice likely has many instances, and it's HA proxy that actually proxies our BFF's TCP connections to them. A request incoming to the BFF will be proxied to one of those microservice instances through HA proxy. But the question is, which one? HA proxy is pretty dumb in this scenario. It's acting in TCP mode. If you make a TCP connection to it, it will make a corresponding TCP connection to one of the microservice instances. It's usually based on some algorithm like round robin, although you can change that. It has no knowledge of how the BFF is using these connections, and it doesn't really care. So on the other hand, our application didn't have any code for choosing a connection either. So this means, again, we have to dig a little deeper into Akka again. So we're back to our host connection pool diagram. Like I said earlier, when a request is submitted to the pool, Akka will send it to an unused connection if there is one. Now, if we take into account HA proxy, that connection slot actually maps directly to a single instance of our microservice. Slot 1 goes to service instance 1. Slot 2 goes to service instance 2. So far, so good, right? So here's the question. What if there are multiple unused connection slots? How does Akka choose which one to use? Well, I didn't find this in the docs, and so I went spelunking through the code. And I found myself at this method. Now, personally, I had to stare at this for a while to figure out what was happening. But you guys are all, awesome functional programming nerds. You know all about tail recursion. So this should be no trouble. But I will save you that trouble. What's happening here is it chooses the first unused slot. Not random one, not a least recently used, the first one. So and it actually says that explicitly in the comments that I very conveniently cropped out. So what does this mean for our BFF? It means that whenever slot 1 is unused, Akka is going to use it. If slot 1 is used but slot 2 is not used, then slot 2 will be used. So you get the idea. We have a bias to use the lower numbered slots. Now remember what I said before, one slot maps to one microservice instance. So we are preferring to use instance 1 over instance 2 and instance 2 over instance 3 in this diagram. Now that's a bit of a problem. Maybe not huge though, right? Because we're only using those hot connections if they're free. But what if that first microservice is really fast at returning a response? Well, then we're going to end up using it all the time because the slot is always free. And when is a server really fast at returning a response? One scenario is when the service is actually overloaded. That microservice, it might have a load balancer in front of it as well. It might be something like Nginx. And it might return 502 really quickly if it's overloaded. There's some queue backing up. It's just going to say 502 really quickly. That's exactly what happened to us. So the first host in the HA proxy list would get overloaded, maybe because it's getting a larger share of the requests anyway. And it would start to return 502s very quickly, so the connection slot was always free. So Akka would keep using that slot over and over and over and make the overloaded service even more unhappy. Is this Akka's fault? Should it be smarter about what connections it chooses? Should it somehow know that a particular host is overloaded and stop sending requests to it? I would actually argue no. You could implement those sorts of load balancing algorithms and health checks into the Akka HTTP client, but it's probably not the best place for it. We already have software that will do these kinds of things very well for HTTP. Of course, that already existing solution is a real HTTP level load balancer like Nginx. HA proxy was, pretty easily replaceable with Nginx in our infrastructure, so we made that switch. Nginx, unlike HA proxy, will actually load balance each incoming HTTP request, not just a long-lived TCP connection. It can also recognize failure responses like 502 and purposefully retry the request using a different upstream service. It can do things like health checking to determine if an upstream is unhealthy, and it can remove it from the rotation for a period of time. This stuff is kind of basic for a load balancer. So it makes a lot of sense to use a load balancer instead of trying to cram all that logic into Akka to do something that I would argue it's not really meant to do. And there's a third logo in the corner there, and that's Envoy. We actually see Nginx as a short-term fix to this problem. Eventually, we want to move to something a little more suited to this role, and that's a service mesh like Envoy. I won't go into details, but look it up if you're curious. So I have to call out one caveat here, and that is that the connection pool implementation has actually changed in the newest version of Akka HTTP. I personally do not have experience with it, so I'm not sure if you can have the same sorts of issues that we saw here. But hopefully these examples have armed you with some knowledge to know what to look for if you find yourself in a similar situation. So that is the tale of Akka HTTP as a routing proxy. With these problems out of the way and solved, it's time to look into Liveness and Akka Streams. So to refresh your memory briefly, here's our system diagram. Our BFFs are consuming Liveness events from Kafka and sending them via WebSockets to our various applications. So let's start with consumption. We're using a library called Akka Streams Kafka. What that does is it combines Akka Streams with the official Kafka client. And personally, I find it really, really useful and very nice. So in Kafka, you consume from a topic. and that topic is divided into partitions. What we need to do is subscribe to all partitions in the topic, because each BFF instance must have all of the liveness data. And this is because an incoming liveness WebSocket is randomly assigned to a BFF. It could request any data. So that subscription is the first few lines. We then simply feed that subscription to a consumer. This is from the library, along with some settings like what host to connect to. And what that gives us is a source of Kafka records. So if any of you are unfamiliar with streaming frameworks, you can think of a source as sort of like a water faucet. It emits elements like a Kafka record, and your job as the developer is to provide functions to handle each element. FS2 is similar. I think they call it a stream or something like that. So you can see that we are providing a map function which simply transforms the Kafka record into its value. Kafka records are key value pairs. We don't particularly care about the key in this case, so we're just discarding it. So now, to do something useful with the source of Kafka messages. The messages are serialized as JSON, so we deserialize them to a case class. Then we send them to a broadcast hub and run the stream. So let's talk a little bit more about this broadcast hub, since it's really the key to this strategy. So a broadcast hub is essentially composed of two parts, a sink and a source. If a source is like a water faucet, a sink is like a bucket. It's how data from your stream gets to the outside world. So the sink half of the broadcast hub takes all of the deserialized liveness messages, but when you run your stream, you get a materialized value, and that value is the other half. It's the source. So every element that goes into the sink will actually be emitted by the corresponding source, but there's actually a very special feature here. The source can be included in as many streams as you like, and each of those streams will receive each element that the sink does. So this is why it's called a broadcast hub. It's like a fan-out mechanism where a single element, like a single liveness event, can be sent to many subscribers. This is, of course, very handy to us. If you think about our domain again, a liveness event can be relevant for many different clients, many different users, or a single user may have multiple applications open that should all get the same event. So back in our code, our liveness source is the source provided by the broadcast hub. The only thing left to do now is somehow filter our source so that we can get a stream of events that are specific to a given connection. Obviously, we don't want to send every event in the system to you when you open your browser. That's not going to scale. It's not secure. So we can define this function that, given an account ID, filters the liveness source to only events that have the same account ID. So you end up with the source of liveness events that is specific to a given account. We could also, substitute user for account or something like that. So one thing to note here, we're not doing any committing of Kafka offsets. What we're relying on here is the default setting of consuming the last message, or the latest message rather. So this code is always going to get the latest events whenever it's run. So this is the Kafka consuming side of things. In production, we do have a bit more code, but all the sort of important concepts are here. We still have to provide these liveness events to our users. So let's take a look at the WebSocket side. Here again, we're using Akka HTTP. Akka HTTP is based on streams, if you weren't aware, so there's some good interplay here. So what happens is, after extracting a request, we can look for a request upgrade header, which is a request for a WebSocket. If that header is present, we can get a source of liveness events specific to the requested account by calling the account source method that we just defined in the previous slide. We then reserialize our liveness events to a string, and then we finally pass that source of now string liveness events to the handle messages with sync source method. So as you can see here, in that handle messages with sync source method, we're ignoring any incoming events from the client side. All we're doing is pushing our events to the client itself. So pretty simple stuff here. I'm omitting some complexity like authentication, which is actually how you get the account ID, but I think probably everyone gets the idea. Who would ship this to production? Are there any problems here at all? Well, there is one small problem. If you try this code out and let's say you add a metric for events being consumed from Kafka, this is what you'll see, an empty graph. There will be no events being consumed at all unless you actually connect a WebSocket client. So what is going on here? The idea is that the BFF should be consuming the Kafka events continually, constantly, so that the new events are immediately sent to any connected clients. There should be no lag between the consumer and what's actually being produced. Well, to the docs we go, and there's this helpful bit describing a broadcast hub. So if there are no subscribers attached to this hub, then it will not drop any elements, but instead back pressure the upstream producer until subscribers arrive. So if we apply that to our situation, if there are no WebSocket clients connected, the broadcast hub is going to back pressure the Kafka consumer so that nothing is actually consumed. This is not the situation we want. In theory, we should have WebSocket connections all the time, but we don't really want to rely on that to ensure that our Kafka consumer continues. So there's a really easy solution to this. Again, it's talked about in the docs. What we're going to do is we're going to connect an ignoring sink to the broadcast hub. And this is just a sink that takes in everything it can and throws it away. So this ensures that there's always at least one subscriber to the hub, and so it's never going to back pressure when there's no WebSocket clients connected. So with the addition of that code, we get a better looking graph like this. Our Kafka consumer is always running, it's always consuming, even if there's no clients attached. Okay, so after all this, is Akka really a best friend forever for our BFFs? Let's take a look at some results. So on our busiest BFF, we're serving 10,000 requests per minute per server. We're also consuming 5,000 liveness events per minute from Kafka and sending 2,000 liveness events per minute per server to our WebSocket clients. These are not like huge numbers, certainly, but like they're decent, I guess. And one concern that people had about this whole pattern actually was that we'd be introducing a lot of additional latency to our HTTP requests. We measured that, and we're only adding about 20 milliseconds to each request. And this includes the additional network hops to and from the BFF and requests to the auth service. So the actual time inside the BFF is extremely small. Finally, the code is pretty efficient. Our busiest machines are running with a pretty low normalized system load of about 0.3, so that's okay. Just to illustrate that last point, some graphs. We're running 3 BFFs on our sort of busiest front end, and we're really only doing that because we want to have some redundancy built into the system. And these are not huge machines either, they're 4 cores. So while doing that, we ended up with a very nice code base. Our BFFs are about 700 lines of code. Most of that is devoted to authentication. And I actually had someone say to me, like, this is the cleanest code base I've seen at the company, which meant a lot to me because I take code quality like very seriously. Now, Akka is not pure when it comes to side effects, but I would argue that the code is still very functional. The side effects are isolated, not with monads, but by injecting the code that does side effects and stubbing it out in our tests. There's 0 mocks used in the unit tests. There's plenty of stubs, but I think there's a good distinction to be made between mocks and stubs. There's also 0 mutable state. That's a great influence from FP. And we've heard a lot about composition during this conference. Well, I would argue that Akka Streams actually shares a lot with other libraries like FS2 in this respect, where various parts of the liveness pipeline don't really need to know about the other parts. You can sort of piece them together to make something useful. We didn't actually see many pieces there, but there are more in the actual production code, and they composed very well. It's also used pretty extensively, composition that is, it's used extensively throughout the authentication code, which I did not show, so you'll just have to take my word for it. So in conclusion, I would say that we're very happy with Akka on this project. You did probably notice that our journey had some bumps along the way, and those bumps had a bit of a theme. So we were writing a very small amount of code because Akka provides these very powerful abstractions. Those abstractions sometimes worked in perhaps surprising ways, especially in corner cases. That surprising behavior was not as surprising, though, once we had thoroughly read the documentation. The Akka Docs are really great, actually, and they explain very well what's happening under the hood of these very powerful abstractions. You have to read them, though. Having powerful tools, whatever those tools are, doesn't excuse you from knowing how they work. So take the time to learn. Take the time to dig in, when you find problems. And this, applies equally to your other tools, whether you're doing pure FP or whatever. You might choose to isolate side effects in a monad, but you still need to know what's happening under the hood. You still need to know what TCP connections are being made and how they're being used. So if writing this kind of code and thinking about these sorts of problems is exciting to you, we would love to have you at PagerDuty. We're always hiring. You can talk to me directly, check out the website, etc. This brings me to the end. Talk. Thank you very much for your attention. I hope you enjoyed it. I'm not going to take questions now, but I would love to chat afterwards. I'll just hang around here a bit. So please do not hesitate to find me in person or online or whatever. Thanks very much.